present to you some recent work that we've done on indolazine donor-based cyaning dyes for near-infrared emissive materials for the purpose of increasing the stoke shift of these materials. So we're going to start off by giving a little background here. What specifically is the NIR? Well, the NIR refers to a region on the electromagnetic spectrum known as the near-infrared, and it's going to run from about 700 nanometers to about 1400 nanometers. And so we're just outside the visible spectrum there and just kind of on the front cusp of the infrared spectrum. And so the reason we're interested in materials that absorb and emit in this region is because they have a lot of different and really practical imaging applications. So I have some of those listed down below here. So starting off, we have night vision. So if you're driving around at night, it's dark out, you can't see anything. And the reason for that is because there's kind of a lack of visible light available. However, there is light available in the NIR region and into the IR region. So if we had a dye, say, mounted on the surface of a camera that was able to absorb that incoming NIR light, then re-emit those photons for a receiver to pick up and synthesize some kind of digital recreation that someone driving at night could see, then we would be able to get a really clear picture of the field out in front of them. With solar cells, the next thing that I have listed, with doing this NIR absorption, this low energy, long wavelength absorption, it would help us if we could convert that into usable energy or some kind of usable fuel precursor. It would make our energy grid more efficient, and so that's what a lot of our other lab is doing, is using these dyes as fuel precursors and things like that. NIR OLEDs. OLEDs stand for organic light emitting diodes, and so very similar to the night vision concept here. If we were to have a monitor or something that was projecting an image, but an image in the NIR region, then it would be completely invisible to the naked eye. However, if somebody were wearing, say, a pair of glasses or something that had the dye mounted on the surface, it would be absorbing that incoming NIR light and then re-emitting it for maybe a receiver in the glasses to pick up, and translate into some kind of digital recreation again that the person wearing the glasses could see, and that would allow them to see then the image on the screen, which was otherwise completely invisible to the naked eye. And then lastly on here, I have biological imaging listed, and I'm going to talk about that a little bit more in the next slide because that's the primary thing that we're interested in with this dye series. So the reason that we're interested in these NIR dyes for biological imaging is because if we look at this diagram over here, the further redshifted and the farther down into the NIR we get, so longer wavelengths, we tend to get deeper tissue penetration, and those longer wavelengths of light tend to interact with tissues less and less. And so the theory is if we get further within the NIR, that light would just completely pass through our bodies. So the idea would be that if we could inject someone with a dye that absorbed and emitted deep enough into the NIR, we could just shine a light on them, have it penetrate the tissue, be absorbed by the dye, re-emit it back for a receiver to pick up, and then again do a digital recreation that, say, a medical professional could use to map internal structures, internal tissues, and things like that. And actually, my father is here sitting in the crowd today, and he works in heart surgery, and they use these dyes on a regular basis to map dead tissues and things like that in heart surgery. So these are practical dyes that are being implemented currently. So additionally, so talking about some of the dye properties here, what we would desire in these dyes, we want to absorb and emit in the NIR for the exact reason I just specified. We want to get that easy tissue penetration. We want to have a large stoke shift, and so if we look at the diagram on the right here, stoke shift refers to the difference in the absorption and the emission peak. So any of that overlap in there is going to be kind of confusing for that receiver to differentiate between, is this just reflected back up that didn't quite penetrate those tissues, or is this actually re-emitted photons? And so that's a narrow stoke shift, a large overlap is going to create for a very fuzzy image, which we have here on the left with these two images. And a larger stoke shift would be the one on the right, so it's going to be easier for that receiver to differentiate and kind of get a clearer picture. We want high quantum yield, so quantum yield simply refers to the number of photons that are absorbed versus those emitted. So if you absorb 100 photons, you re-emit 10, you have quantum yield of 10%. Molar absorptivity, that's just the amount of photons that you're absorbing in a given concentration. And molecular brightness, the fifth thing we have listed here, is just kind of a combination of quantum yield and molar absorptivity. So it's just those two factors times each other. And it's going to give kind of a good measure of how efficient is this dye, how many photons is it absorbing, and then what is it doing with those photons. And then last but not least, despite how hardcore of an organic chemist you think you might be, none of us have DCM pumping through our veins, and so we need these dyes to be water soluble because we are all made of aqueous solutions. So why are we interested in the cyanines? Well, I mentioned that they're already using some of these dyes in practical settings and things like that, like medical settings. And so the dye that they're using right now is indocyanine green, and that's kind of the staple market dye that a lot of people are looking towards right now and using. So if we go through that checklist and we look at ICG, we can see based on its absorption and its emission graph down here, we're absorbing around upper 700s, maybe up to 800 nanometers. So that's in the NIR region. We're emitting at around 830 on average. So that's going to give us our stoke shift right here of 31 nanometers. Quantum yield is 9.1%. That's really good for these dyes. Molecular brightness, or molar absorptivity of 238,000. That's really good for these dyes. Both those factors being high are going to give us a high molecular brightness. And then these sulfate groups on here, that's going to make it water soluble. But if we look back at that Stokes shift again, only 30 nanometers is considered to be not very good for these materials. So although ICG does meet a lot of criteria, it's kind of lacking in that Stokes shift, and that's what we're looking at increasing with the cyanines. And so the reason that we look at the cyanines for increasing the Stokes shift is because if we look at ICG, it's a completely planar pi system, and that means that going from the ground state to the excited state and back down to the ground state upon absorbing and emitting those photons, it's going to have a small reorganization energy, meaning that the emission energy is going to be fairly close to what it absorbed, and so it's going to have a small Stokes shift. Whereas with these cyanine dyes, we knew that there would be some steric strain in the pi system, looking at some of the computational data on these. And so that steric strain is going to create an issue going from the ground state to the excited state back down to the ground state. And so there's going to be a larger reorganization energy here because it's having that steric strain, and that's hopefully going to give us a larger Stokes shift, is what we were interested in primarily seeing with this dye series. So synthesizing these materials, I have an example synthesis up here. I have a full synthesis at the end that was in the paper, if anybody would like to see that. We start off with our ethylpyridine, and we run an alkylation reaction with this bromophenylethanone in acetone. We allow it to reflux overnight. It yields an intermediate salt that we then filter off and combine with sodium bicarbonate in water, and we allow it to reflux for another couple hours, and that's going to cyclize and yield our indolazine product. We then take that indolazine, and this is where we get our different syntheses here. This first molecule on the top left here, that's our cyanine linker, and that varies from if we want a 1-carbon bridge between the donors, a 3-carbon or 5-carbon bridge. And so that's going to vary, but this is the one for the 5-carbon, and we're going to run that in the presence of acetic anhydride, perchloric acid, and triethylamine, and that's going to yield our dye. So we were interested with two things whenever we looked at this dye series. We want to know what the effect of increasing the carbon bridge between the donors was, and we wanted to know what the effect of placing various substituents around the molecule was. So we're going to start off with talking about the effects of increasing conjugation. So with the C1 dye, if we look at its absorption down here, we're absorbing it around 600 nanometers out to around 650, so it's not quite into the NIR. If you remember, I said that that was started around 700 nanometers, so we're not quite in that near-infrared region yet. However, if we look at C3, we're absorbing a little bit above 700, so that is starting to get into the NIR. And then with C5, we're all the way out to 800, 830, 840 in some instances. So that is in the NIR fairly deep. Additionally, increasing conjugation. So going from the C1 to the C3 dye, some of those other factors we talked about, we have molar absorptivity here on the top. We're going to see that greatly increase going up to the C3 dye. We're going to see our quantum yields increase as well, and because of that, our molecular brightness is going to increase because it's both those factors kind of combined. However, we are going to see a rapid decrease in our Stokes shift, and that's because the C1 dye had this really interesting dual emission property in certain solvents. So there was a first emission peak along with a second emission peak, and we never really figured out why that happened. We didn't look into it too much. But going from the C3 dye to the C5 dye, we're going to see that molar absorptivity kind of narrow in on both ends. We're going to see our quantum yields increase again. We're going to see our molecular brightness increase because of that. And we're going to see that Stokes shift pick back up. So C5 dye is ultimately what we were most interested in. And so then we want to see also the effect of placing various electron donating and electron withdrawing groups around certain positions on the dyes. So atop the phenyl ring, we place an electron donating methoxy and an electron withdrawing cyano, and then at the base of the indolazine we have again that methoxy group. And so ultimately there's some slight variations between these electronic groups. So if we look at the cyano, we can see that Stokes shift is much larger than what the methoxy gave us, the top methoxy. We can see that our quantum yields vary a little bit, molecular brightness varies a little bit, but ultimately the main conclusion that we had from this was that these positions were kind of weakly tunable and didn't do all that much for our dye series, or at least as much as what we were hoping we would see with these electronic substituents at these positions. So also, based on the data I just showed, some of you might have picked up on the fact that our quantum yields are significantly lower than ICG's. Ours were around 3.5% of their max. ICG was around 9%. And the reason for that being is because we tend to see this trend as we get further redshifted in the NIR based on the energy gap law, that as we're doing this lower energy absorption, this longer wavelength absorption, it becomes easier for those dyes to lose that energy just through thermal relaxations or vibrational means, rather than actually re-emitting a photon. So the fact that we are further redshifted in the NIR is working against us there. And additionally, I talked at the beginning about how we wanted to increase our reorganization energy in order to increase that Stokes shift. As we widen our reorganization energy band and we start doing that lower energy emission as well, it simply becomes easier just to lose that energy as heat as well as just vibrational means instead of actually re-emitting a photon. So we kind of had two factors working against us there, and it was a trade-off that we kind of had to make in order to increase our Stokes shift we kind of knew going into this that we might see our quantum yields drop off, and we might, due to both those factors, because we are going to be more redshift, and we are trying to increase that Stokes shift and increasing our reorganization energy. So lastly, kind of in going forward with this, if we looked at where we placed the electronic substituents before, if I run back 2 slides here, we have the groups at the top of the phenyl ring and at the base of the indolazine. And so if we look at our homo-lumo diagrams here, on the C5 guy specifically, because that's where we were placing these groups, there's not a lot of electron density around there. There is some, but there's very, very little. So placing a substituent there isn't going to be very electronically significant. And then if we look at the electrostatic potential diagrams here on the bottom right, if we look at where we placed that substituent at the base of the indolazine, the red would be where the electrons are being withdrawn from in the ground state, and the blue areas would be where they're going to in the excited state. We can see there's a little bit of red and a little bit of blue down there, but there's not too much. It's mostly fairly green, which is showing neutral electron density. And so ultimately what we conclude from that is that neither one of those positions was very electronically significant, and that's probably why we didn't see too much tunability in terms of placing things there. However, if we look at the side of the C5 indolazine, where we currently have this, this methyl group right here, if we go down to our electrostatic potential diagrams again, we're going to see that there's a very, very large red spot there. And so we believe if we could swap out that methoxy or that methyl group for some kind of electronic substituent, we believe that that would actually increase the tunability of these dyes and maybe have a larger effect on changing up our quantum yield, changing up those Stokes shifts, something of that nature. And so for future synthetic routes, that might be something that we would look into, would be getting some kind of electronic substituent there at that position. So I would like to acknowledge some of the people that helped to make this presentation possible. So obviously our funders, Mississippi EPSCoR, the National Science Foundation, and the Honors College at the university also provided some funding for these projects. I'd like to thank all the group members. We have many of them pictured here below, and all the people that helped as collaborators to help write the paper that was recently published on this work. Jack Legaden, that's the graduate student that I work with. Shane Outry, he does physical chemistry for us in Coulter as well. Dr. Blake Hill from JSU, Dr. Sean Parkin from UK, Nathan Hammer from the University of Mississippi, and Dr. Jared Delkamp, whose lab I happen to work in. So, thank you very much.
Yes, sir. So if you use the technique of two-photon absorption, you will get an emission, you'll get an enormous Stokes shift, and also you will get the emission in the visible. So you take your light source in the infrared, you illuminate the dye, and it's, instead of emitting more into the red, it's going to actually emit into the blue. That's two-photon absorption. And that's an enormous Stokes shift as well. Why don't you use that technique in the medical field?
I would believe that would be because if you're emitting in the visible spectrum, it's going to have issues making it back out of the body as well, because talking about getting that tissue penetration. If we go back further blue shifted, it's going to be less able to make its way out, similar to if it, similar kind of how it had to be redshifted in order to make its way into the body. It would have a hard time getting back to that receiver.
So the light source for that, do you know the light source for the two-photon absorption?
I don't know.
Yeah, it's a laser actually, and
okay.
Kill your patient.
Oh, no.
But what you said is also true.
Okay. Yes?
Yeah, I was wondering about, we talked about the quantum yields.
Mm-hmm.
Are they all in the same solvent?
The solvents kind of varied from dye to dye, but I think those quantum yields were averaged to kind of give us an average of what we were seeing there.
So for your dye, I assume that was some organic solvent.
Yes, yeah, some organic solvent.
The one for ICG though, 9.7%, that's water?
It would have been water, yes.
Okay.
And actually recently we did find a way to place sulfate groups on these dye series, so
okay.
We might be getting some imaging data here for these dyes.
On the 5 position of that?
Yes.
Off the indole?
No, off the top of the phenyl ring, sir.
Oh, okay.
So that would draw it into water.
Great, cool.
Change it to imaging. Because ICG actually did have similar quantum yields of things in organic solvents, and then placing it in water, we did see they observed a large increase in the quantum yields and things.